Hello everyone, good morning and welcome to Sarat Chandra IAS Academy where your dreams are our mission. This is Yatharth here. In today's lecture, we'll be specifically covering the space terms, space topics and what's new in the research. So this has been a favorite topic of the UPSC in the last few years. A PYQ also was asked in 2023, so we'll be dealing with that also in the beginning only. Alright, so in this single lecture, I'll try to cover most important things that can be helpful for this year's prelims. All right, let's first go to the PYQ that was asked the last year only. So it was asked that consider the following pairs. So match the following basically. Cepheids, a giant cloud of dust and gas in this space. All right, so whether it is correct or incorrect, we have to figure out. Then nebula, stars which brighten and dim periodically. And then pulsars, neutron stars that are formed when massive stars run out of fuel and collapse. All right, so we need to see that do these things match or not, or basically how many pairs are correctly matched. Okay, so we'll see that later on as we learn more and more in this running video. We'll definitely come to a conclusion by the end that how many pairs are correct. All right, so let's figure out that what we are going to cover in this video. First of all, we'll be talking about the elementary particles to begin with, which make the matter in the world. All right, then we'll be talking about the basic structure of an atom. So this is the most basic stuff that we need to know. And it plays a part everywhere. Recently, we did a lecture on the nuclear program. So there we saw and talked about the nuclear fission. So I explained the fission as well as the fusion there. So both these processes talked about the atoms, neutrons, proton, electron, so on. We also talked about the uranium, thorium, all right, plutonium. So many things we see in daily life and our UPSC syllabus also. So we need to have a basic understanding of all these things. Then we'll talk further about the proton, neutron, electron, and quark particles. So these quark particles are the particles of now, particles of present. Okay, these are the most debated particles in the present. Okay, so these are the ones which give rise to various different things like quark stars. Okay, and different topics in the prelims. So we need to know about them. Then fundamental forces of nature. We'll just be talking about simple electromagnetic forces, electrostatic forces, magnetic forces, gravitation forces, so on in very small. Okay, in brief. And what are the quark particles and quark stars? What are stars fundamentally and about their life cycle? The PYQ that you saw came from this topic. Alright, you will find both the options, whether it is a nebula, whether it is a pulsar, in the in this topic. Then we'll talk about our star, that is sun, most important thing. Alright, usually question comes on this. In 2022 also question came on this. Then we'll talk about the future of these discoveries and PYQ solution at the end of the video. Alright, so let's begin with the first thing, that is standard model of the elementary particles. So what are elementary particles? Elementary means which cannot be divided further. Which cannot be divided further. And at least this is what we know as of now. Okay, there was a time when we thought that atom could not be divided further. Okay, but we discovered that it is consisting of protons, neutrons, and electrons. Then there was a time when we thought that protons and neutrons cannot be divided further. But we discovered that even the protons and neutrons are made of various different leptons, whether it is, let's say, or quarks. So whether it is a quark particle plus gluon. Okay. So whether it is a quark particle, then we came to know that these quark particles are also up, up, down, then strange quarks, and so on. All right. Strange quark, charm quark, and so on. So this is the thing about science, that it is completely dynamic. It is completely dynamic, and no definite or objective statement, let's say final statements, you will find in the prelims. But what we need to see, that what we know as of now. So this is the standard model of elementary particles we have as of now 2024. So what do we know? That there are three generation of matter particles or fermions. Okay, so these particles, what is the difference between them? These are basically the heavier particles. As we go from three generations, these are the heavier particles. So up quark, these are the quark particles. They are divided into two things, quark and leptons. Okay, so these are the quark particles. Quark particles, these are the light quark particles, and these are the heavier quark particles. Now they keep emitting energy and come back finally to the first generation materials. This is why most of the matter is first generation or made of the first generation quark particles. Okay, these quark particles also exist in the world, but they are harder to study. This is what we will be seeing. Okay, then these are interaction particles, interaction or force carriers. Okay, one of the very major force carrier we have is photon. It displays both type of let's say characteristics of a particle also and a wave also, and a particle also. This you must read about. Okay, it was explained by Einstein in his Einstein equation of the photon. All right, these are the gluons. These are the force carrier which keep the particle stick to each other. Okay, if let's say proton is made of, let's say, three quark particles, whether it is up, up, down. Okay, so what is making these particles stick? Then it is a hypothetical particle known as the gluon. Okay, one more thing that we need to see, just a second, is that when we talk about the particle, we are not saying that these are like this ball. Okay, we do not completely understand that what particles actually are. They do not have a shape. What we finally see, they have a probability of being found somewhere and some sort of energy. Okay, we can only see them as energy. So when we talk about particles, we may or may not know that whether they have a definite shape. All right, so when we are saying about gluon, it could just be an energy. It could just be an energy, not actually a particle. Okay, so this is the basic fundamental understanding when we go towards the elementary particles and so on. Okay, this was the Higgs boson. Very cool particle, no charge, no mass, but still has something to do with the energy. Okay, so it was also termed as the God particle because without this Higgs boson, we would not exist at all. Okay, we are all made of atoms ultimately, somewhere carbon, some iron, some magnesium, whatever is there. Okay, so where all these elements come from? These elements all come from stars. So we'll be talking about stars as well. Right now, what we need to understand is that there are two, three different type of particles, simple particles, leptons and quarks. So leptons are different from the quark particles, such as electron, muon. Okay, and these different, but the major lepton that we have is electron. They carry the energy and have less mass. All right, and these are gauge bosons. We do not have anything to do with them right now. Just focus on the quark and the electrons. All right, all the other particles, let's say protons, neutrons, they are not elementary particles. They are made up of these quark or electrons. All right, so we'll be talking about them also. Okay, so here we see the generations of matter, such as the quark. These are colored particles and leptons are color-free particles. Now, what are color particles? What are color particles? So color particles or color energy is a different branch of these, let's say, elementary physics. All right. We do not need to study about this. We can just say that the charges, the nature of charge or nature of energy transfer between two particles or even the same generation of a particle of, let's say, two quark particles. Okay, emits some charge, emits some energy, or this nature of this energy emits some color, you can say. Okay, when the energy is transmitted between these particles, some color goes on. We can see some sort of color. So this is a different branch of science and physics. So we don't need to know about this, but we can just say that based on the nature of the energy that these two particles have, they are divided into two categories. One is the quark, one is the lepton. All right. Now quark have two types. They are down type and up type, up up down or down down up. But basically two types, up and down. All right, there can be anti-quark also or so on. Okay, now these subtype is divided into three generations: down, strange, bottom, and up, charm, and top. All right, so up, down, strange, charm, and bottom, top. These are the three types of generational pair. What is the difference between these generational pair? That they have more mass and energy, they have less, and they have the least. They are the lightest one. Okay, and they keep converting from here to here. but these are also formed. The bottom top type of the quark particles are also formed, but only in extreme condition, only in extreme temperature and extreme pressure. So only when the stars are formed or something like that happens. Okay, the common mass is made by these first generation quark particles, such as the simple protons, simple neutrons, and most of the matter in the world is made by the first generation quark particles. All right. Now we see the leptons, which are color free. Okay, they are different from the quark particles entirely, and the electron is the major example. So just say, remember that electron is a lepton. Electron is a lepton, not a quark particle. It is not made by any sort of quark particles. Okay, it is just an energy particle with a mass and magnetic moment. All right. Now let's come towards the atom. One thing we see that the current model of atom we know, we cannot see this. Okay, this is a hypothetical model. We can just see the energy flying here and there like waves. Okay, let's see, we make this orbital. So what we see that when we do a graph, when we make a graph like this, so it comes like this. Okay, so what we see that energy of the electron can be seen least here and again least here and the most here. Okay, so this we term as an orbital. This we term as an orbital. That this is an orbital, electron goes here. So this is what this orbital is showing. This is the electron. All right, inside the nucleus. So there is no nucleus, of course, such as there is no definite wall in the atom. Okay, there is a wall here. Okay, there is no wall. It is just a definite area where we find the most of the mass of the atom concentrated. Okay, so it is proton plus neutron, and they are bound by electromagnetic forces. All right. So this is the nucleus. Nucleus does not exist in real life. It is just an area of the probability where proton and most of the mass of the atom is concentrated. Then there we see these electrons. Okay, electrons also, this orbital do not exist in real life. This is just an area of probability as per the quantum mechanics. Okay. So please do not think that there is some sort of atom. It is just basically like this where we can see the particles. Okay, an area, and here we can see the waves of electrons of energy. All right, this is neutron. This we see in the blue. Then there's a proton, and this is the orbit or orbital. There are orbits. Then there are orbitals also, small orbitals. Okay, let's say this is s orbit or p orbit. Okay, then this has p further orbits, p1, p2. Okay, p has 3 orbits, s has 2, then d has 5. Okay, you must have all in the 11th or 10th class, you must have heard about the electronic configuration of any element, of any atom. Then you must have read about 1s2, 2s2, 2p6, all right, 3s2, 3d10, and so on. Okay, so electron goes in the orbital like this as per the current studied model. All right, now let's talk just about the proton. What do we know about proton? Positive charge. The positive charge of any atom comes from the proton. Okay, so protons are extremely small. All the particles are extremely small when we are talking at the nuclear level, and they have a mass of 1.67 10 to the power minus 27 kg. Very, very small mass. Okay, but still 8,000 times heavier than an electron. Okay, their charge. So we already know the charge. It is 1.6 into 10 to the power minus 19 coulomb. This is coulomb. Okay, very small charge, but still positively charged. Okay, now we see the location. And please do not confuse the smallness or miniature charges as being insignificant. They are very, very significant. These are the things that have made the world and everything around us, from the Eiffel Tower to Taj Mahal to our own bodies. Okay, because even a single atom has so many protons. It has so many protons. Even a single atom we are talking about. All right. If you go to a desert and take the sand, okay, in your, let's say, hand, your palm, then your palm will have more atoms of the sand than there are stars in the galaxy. Okay, so their size is extremely small. Now we talk about the locations. Protons are located in the nucleus of an atom. Nucleus, as I told you, does not really exist like a boundary or something. It is just an area. The nucleus is densely packed and make up the overall mass of an atom. Okay, because all the protons and neutrons are residing into that. Next, we come to the discovery. Very important. Okay, discovery is very important. Please remember, protons were discovered by Ernest Rutherford in his Guildford experiment. Okay, you can see about the Guildford experiment. Basically, it was just a machine where some atoms were kept a very thin gold foil was inserted at the end, and some cathode rays were, cathode or anode rays, I do not remember correctly, were just transmitted, and he saw that where the most of the mass of the atom is falling, okay, many of the rays did not occur to, let's say, penetrate this middle thing. Okay, you can read about this gold foil experiment. It is in 10th or 11th class. Now we come to the composition. So protein are made of elementary particle called quarks. Okay, different from the leptons. Leptons basically electron and multiple things. So they are made up of quarks. The proton is made up of two up quark and one down quark. Okay, so plus 2 by 3, two up quark and one down quark minus 1 by 3 electron. Okay, the overall charge of a quark is lesser than electron. It is 1 by 3 of an electron, down quark, and positive or up quark has positive 1 by 3 charge. So it defies the theory of the singularity of charge. Even the quark defies the theory of singularity of charge. Please just remember. Now let us come to the important portion, that protons are responsible for the atomic number of an atom. The number of proton in an atom is the atomic number of that atom. Okay, so let's say you talk about the aluminum. So it's 13. Okay, that means it has 13 protons and 13 neutrons in the normal state. Again, we come to neutron, nothing different from proton. Nothing different from proton. Just the positive charge is not there. Positive charge is not there. So neutrons are extremely small, again have a mass of 1.67 10 to the power minus 17, the same mass as the proton. Charge neutral. Okay, positive charge is not there. We'll see why it is not there. So location, they are located same place, nucleus of an atom, and discovered by James Chadwick. James Chadwick. Please remember. All right. Composition. So we see that it is made up of one up quark, that is plus 2 by 3 charge. Okay, and two down quark, that is minus 1 by 3 charge. So what difference we see? That if it is an up down quark, up down 3 quarks, then it makes a proton. If they are down quark, then it makes a neutron. No other difference. Alright, just the nature of the quark changes. One up, one down common in both. Just one up and one down changes. The nature of the quark changes. Okay. And what do they do? That neutrons help stabilize the nucleus by binding to the proton, which stabilize the repulsion forces between protons. Alright, again, very, very important. Because if there are so many protons in a nucleus, they are all positively charged. Okay, they will repel each other. What do we need? The neutrons between them. Okay, so that they do not repel each other so vastly. And now we come to the electrons. Electrons are leptons. Electrons are leptons. And what is made up of quark? What is made up of quark particles are usually hadrons or baryons. Hadrons or baryons. Okay, hadrons have 3 quark particles. Just now we saw up, down, like a proton, and up, down, like a neutron. So all of these are hadrons. We'll see this later. But and now we eliminate quark altogether from this discussion. We focus on the leptons, that is electron. Okay, so electron is very different from a quark particles. So they are negatively charged particles that surround the atom's nucleus. Electrons were discovered by J.J. Thomson in 1897. Remember the plum pudding model. Okay, what was the plum pudding model? He said that basically if you make a pudding, okay, then they are distributed like the plums in the pudding, or multiple different models can be made. He just said that randomly electrons are present in an atom. So electrons determine the properties of the atom. Chemical reactions involve sharing or exchanging electrons. Okay, let's say one electron is going here to there, then a covalent bond is forming. Okay, because they want to stabilize, all of the atoms want to stabilize. All of the reactions, everything in the world is aimed towards one single thing, reduction of the entropy, reduction of the randomness. Everything wants to reach a final state by burning its energy. Alright, that is the law of the world. So what we see, that electron is a stable subatomic particle, negative electrical charge. Unlike protons and neutrons, electrons are not constructed from even smaller components. Okay, so they are different elementary particles made up of nothing. They are itself the elementary particle. Electrons are found outside the nucleus. They are not free, however, they are still bound by the force of nucleus, bound by the positive proton force of the nucleus. They cannot just simply escape whenever they want. Okay, we'll have to give the atom extra energy to make them, let's say, go away. So mass of an electron is 9.10 and 10 to the power 31 kg. So that is even 8,000 times less than the proton. So this is about 1 upon 1836 the mass of a proton. Sorry, 1,000 times of the proton, or 2,000 times of the proton. All right. Now let's come to the most important thing we have today, that is quark particles. So quark are the only elementary particles to experience all the known forces of nature. Okay, why all the known forces of nature? We'll see in the next slide that what forces of nature are there. Okay, but to experience the force of nature, one has to have two properties. One, it has to have mass, it has to have electric charge, or it has to have a magnetic moment of some sort. Okay, and to have a fractional electric charge. So one thing we see that they have fractional electric charge. We saw 1 by 3, 2 by 3, or positive 1 by 3 and negative 1 by 3, and so on. Okay, they all have, such as the up quark, it has positive 1 by 3 charge. Down quark, it has negative 1 by 3 charge. All right. So they are the particles that defy the singularity of the charge sort of theory. Okay, the interaction between quark and gluon is responsible. Gluons are these particles. You can see here, these are the gluons. Okay, and they mediate the force binding them together. Why do we need, let's say these are two up quarks. Okay, they are both repelling each other. They have both have positive charge. They do not want to come close to each other. So we need a stronger force here. Okay, now there is a repelling, attracting force between these up quark and down quark, because these are positive charge, this has negative charge. So what do we need? A different sort of gluon here, different sort of force here. Okay, and these have to mediate the balance if they want to create a proton. So this is a proton. All right. Now what we see is responsible for all the perceived mass of protons and neutrons, and therefore where we get our mass from. These are the elementary particles, the quarks. These are the particles which make the world completely. All right. Now let's talk about the forces of nature as well as hadron before we go towards the stars. So what we see that hadron feel the strong nuclear force. Basically, two type of particles. One are mesons and one are the baryons. So baryons are three quark particles such as up up down or up down down. So basically protons as well as neutron, explained this earlier. Then we see the mesons. Mesons are nothing apart from two quark particles such as the pions, kaons, and so on. That means up and down quarks. Okay, this down quark is a strange quark or charm quark, maybe from the second generation of the quark particles. Okay, now let's come to the forces of nature, fundamental forces of nature. So what we see in nature, there are four fundamental forces. Four fundamental forces. What are these four fundamental forces? There are four fundamental forces known as, first is gravitation. Gravitation. Second is electromagnetic force. Electromagnetic force. Third is the strong nuclear force. And fourth is the weak nuclear force. Okay, there are four type of forces in the world that govern the basic world. And we have still, even in 2024, we have not yet occurred to form a single theory that explain all these type of forces. We do not know that how gravitation works in such long distances. Okay, even the let's say the farthest star of the galaxy and you have some connection with the farthest star of the galaxy which exists right now in the present. All right, because it has some mass, you have some mass, and you have some distance, and that is all we need to make the gravitation work. The formula of the gravitation is G m1 m2 upon r square. Okay, so if you have mass, if the thing has mass and there is a finite distance between them, then there will be gravitation force existing between both these things. Okay, you and I also have a gravitation force working between us. But when we go to the small nuclear distances, the gravitation is not the one that is keeping things together, because gravity is not very strong to keep two protons bind to each other. Okay, so what we need here is the strong nuclear force, and it is 3 trillion times stronger than the gravitation force. Okay, we see the electromagnetic force. What we see that whenever there is a charge traveling, electron or any charge traveling, then it will also create a magnetic wave. Okay, and whenever there is any magnetic, if you move a magnet here and there, okay, then it will create an electric charge. These both forces are intertwined somehow, You cannot separate electricity from magnetism. You cannot separate magnetism from electricity. Okay, both of these forces are combined with each other. So these are the four fundamental forces of nature. And the quark are the sort of particle which take part in the formation of proton and neutron also. So they feel the strong nuclear force also. They take part in the let's say building of the proton and neutron. So they feel the weak nuclear force also, and gravitation also, and electromagnetism also. Okay, so there is a statement if we say that quark are the only particle that feel all four fundamental forces of nature, then yes, it is true. All right. Now let's come to the second thing. And one more thing, please remember that these quark particles are very dynamic. They can change a neutron to a proton, they can change a proton to a neutron, and so on, because they are the ones that making these neutrons and protons. And this is just reaction. A neutrino is evolved, and a down particle is sent, down quark is sent, and a neutron can change into a proton, and so on. Okay, these are the reactions that are going on in our stars and sun. So next, let's come to the important thing. Again, a very important topic. What is a star? Okay, so a star is a celestial body. Celestial body means found in space, and it is made up of gas particles. So what we say when we talk about the gas particles, we say that regardless of however deep we go in a star, we will not be finding the solid state. Gas is just a state of particles. Does not say or mean that it is just like a gas flying in a room, that you won't be seeing it. It does not exist. Okay, it does not mean like that. Gas particles means all of these particles are a little bit away from each other and far enough to not create a solid or liquid state. But in the end, in the subatomic level, we see that there are still multiple forces working there. Okay, so it is that shines by the radiation derived from its internal energy sources. So as I told you, if the core of a star has heavier things such as helium, then they are wanting to change into hydrogen. All right, and the energy is releasing constantly, then it means that this energy is making the light that is coming out of the star. So our star is the sun, our galaxy's star is the sun. So the main characteristic of star are such, they are self-luminous. They use hydrogen gas as fuel and they rotate around their own galaxy. It is not completely true. Okay. They use mostly the energy that is emitting from the fusion. So let's say there is hydrogen here and it wants to convert into helium. Okay, more stable. Then it will release some energy in the nuclear fusion because of extreme pressure and extreme temperature. All right. So they are using hydrogen gas as fuel. So when we talk about our own galaxy, we see that the sun is our star. Okay, sun is the star of our galaxy. And there are lots of stars in the universe, but sun is the closest one to the earth. So stars come in a variety of sizes, from smallest to largest sizes. They are called white dwarfs, main sequence stars, giants, and supergiants. Okay, one star can also turn into a supergiant or giant later in its life. Okay, now let's come to what our PYQ was dealing with. Okay, so let's start and focus on the life of a star. So life of a star usually starts from a nebula. Okay, nebula is what? Nebula is what we initially was thinking. It's a, let's say, collection of dust particles in space and gaseous particles. Now this gaseous particle can be of multiple things. It can be of hydrogen, it can be of helium, it can be of iron, it can be of various different things. They decide what this star will ultimately be made up of. Okay, now what happens? It gets some external energy. Some energy comes flying to it. Okay, it can be from any other source such as a supernova explosion nearby. Could be because of a black hole formation nearby, could be because of merging of a black hole. It could be because even of a, let's say, collapsion or the collapse of a galaxy, nearby galaxy. But ultimately it gets some energy. Okay, this energy does what? It creates the force of attraction here in this region of the space. It creates a force of attraction. Because of the attraction, what happens? A nebula turns into a dust cloud, more attracted, more compact. Okay, and as the electromagnetic forces or the nuclear forces overpower the gravitation force or the repulsion force, or we can say actually, when the gravitation increases rather than the nuclear forces that are separating these particles from each other, then it becomes even more compact. Okay, it becomes or turns into a globule from a dust cloud. So what we saw, the initial stage was nebula, then a dust cloud, then a globule. So gravity is more here. Gravity is more here. It's increasing. So with the star's life, the gravity usually increases. Furthermore, it becomes a protostar. It becomes a protostar. Protostars mean it starts taking a definite shape. It starts taking a circular spherical definite shape. Alright. Next we see that it can follow two parts. It can either make into nothing. Alright, it can make into a small star by releasing some energy. Let's say energy is released from here. It becomes a brown dwarf. Okay, second path mostly it follows 80% of the time it follows another path where it becomes a main sequence star. That means it keeps on attracting more dust, more things into it and increases its own gravity. Increases its own gravity. It can further become a red giant. All right. So our sun is into this position now. It's a main sequence star. But furthermore, what happens that energy keeps on releasing, and it becomes a red giant. Okay, because gravity is lessening now a bit, and it can expand into the size. All right. Now what happens finally? It releases material in the space. Material is released in the space. Okay, and these heavy material, heavy particles are released in the space, and what happens further? That it can become a white dwarf. It can become a white dwarf star. Okay, so after the material is released from a main sequence or a supergiant star, it may become a white dwarf. Furthermore, if the process keeps on continuing, if there is no energy left, no material left, only gravitation left, then it can become a black dwarf. Okay, whatever material is left, it becomes constrained into a very small space, then it is known as the black dwarf. Finally, what can happen that if it does not become the black dwarf, there is still energy and material, it can go into a bang. Okay, this bang is known as the supernova. All the energy is released. Okay, all the material is released sometimes. Okay, now whatever material finally is still remaining, let's say 10% material, 20% material, okay, which cannot escape the force of gravity. Okay, so it is deeply condensed, deeply condensed. The density increases a lot. So as per the supernova, whenever there is an explosion, it can also give birth to a new star in a separate space. Let's say this energy goes into any nebula and it makes a new star. Okay, but it has three options from here. One, it can become a neutron star. It can become a neutron star. So only the neutrons of the star are remained here. Only the neutrons of the star are remaining here. The protons convert into neutrons by release of energy. Okay, so only the gravity, very harsh gravity remains here. So it can make a neutron star. Second option it has, it can even become a black hole. Okay, the death of a star can make a black hole, but it not always, only sometimes. Okay, however, always, let's say the neutron stars when convert into black hole eventually. What happens in a black hole that we actually do not know a lot about black hole, but we know some Hawking radiation comes out of the black hole also. Okay, so all energy is never depleted. Even in a black hole, all energy is never depleted because there is Hawking radiation coming out of the this curtain of the black hole or the border of the black hole. But what we see that gravity is a lot. Even the light cannot escape this gravity. That is why it looks black. We do not actually know what is. There is nothing actually inside a black hole. All right, there is nothing inside a black hole. It is not like a hole that you can go inside. It's not like this. Okay, what we see that black hole is basically we cannot see this. So basically, it's a star very densely packed, very densely packed. There is nothing actually inside of a black hole. You will just get sucked if you go into this. A black hole is like this. It's still spherical. Okay, this is what you see because when you see a sphere like this, it looks like a circle because if there is no light or shadow here, okay, it's still a sphere. You cannot get sucked into this and let's say exit into some other pathway or through a white hole. Okay, it doesn't work like this. It's just a spherical body in the end. You will just get sucked into the nucleus of that body. Okay, and next we see that it either ends with the black hole or it continues forming. The energy keeps continue forming into a nebula. So this is the life cycle of a star. Next, we see our own star, that is the sun. So sun is the star of our galaxy. It because of its own gravity, it has multiple planets revolving around it, and it also revolves around the center of its own galaxy. Okay, so this is the sun. Sun is the main sequence star. Sun is a main sequence star. and it may further turn into a supergiant. Okay, this is what we are all afraid of when it completely consumes its own helium and hydrogen. Okay, so it's using hydrogen as fuel. This is the core of the sun. It is the warmest, hottest thing. Okay, gravity is the most here. Gravity is the most here, and fusion reactions are going on. Okay, you can read separately about the sun. Basically, there is a photosphere, chromosphere, and so on. And solar flares are always coming out of the sun. Solar flares, and there is solar wind also. So a question also came on the solar winds. And now let's quickly go to the neutron star and strange quark stars. So what is the difference between this? We already know neutrons are composed of the quarks only. Okay, neutrons are composed of quarks only, such as the up, down, down quark. So something, let's say in a life cycle of a star, it becomes like a neutron star. Okay, this is the neutron star because in the core there are only neutrons here. In the core now, all material has gone, evaporated. All rest of the energy is gone. Okay, very strongly compact star is remaining. Very strongly compact star is remaining. Very small, first of all, but very high density. Density is very high. All right, almost solid. So what we see that in the core there are neutrons. Now what happens even if these neutrons do not exist? Okay, these quarks come out of the neutrons. It exists as a quark. Okay, so it becomes a quark star, even denser than a neutron star. So a quark star is a hypothetical type of compact exotic star where extremely high and core temperature and pressure have forced the nuclear particles to form quark matter, a continuous stage of matter consisting of free quarks. All right, so different stage of matter. We do not completely understand or know about this. We just know that multiple quarks can exist in free, let's say, continuous stage like this in a quark star, but we have not yet seen a quark star or come across it. All right, so what is the difference here? That here we see the neutrons in inner core of a neutron star. We see the neutrons. This is why it's known as neutron star. Okay, but we know that neutrons are further made up of quark particles. Neutrons are hadron, and they are made up of quark particles. Okay, the elementary particles. So we see that in the core of a strange quark star there will be electrons and up, down, and strange quarks. Okay, what we see that there will be quark particles, various different quark particles, further continuing the let's say degeneracy of a neutron star. So degenerate electron layer. Okay, so you do not need to read a lot about this. Just know that a strange quark star can be a further decomposition of a neutron star, even more densely packed, and has in its core a continuously existing state of matter known as the quark stage. Okay, very important. Now this there is an equation, the Tolman-Oppenheimer Walk-off equation. Very important equation, very complicated, and the minds of like us cannot understand this equation. Uh, Given, let's say, we do not have enough time to understand this also. So probability to the presence of quark within the neutron star. This equation displays that what is the probability of the presence of quark within a neutron star. Let's say in the neutron star the core is made up of neutron. So you keep increasing the pressure, you keep increasing the temperature of the core, it will eventually degenerate into the elementary quark particles, like a pressure cooker. Okay, it's like a pressure cooker. So in pressure cooker, what happens if you keep increasing the pressure and temperature? Things break down. Okay, even if you keep, let's say, even if you leave rice for 1 hour, it will just melt. Okay, become nothing. It will become like a slurry. So this is what happens in the core of a quark star. The neutrons becomes like a slurry of the quarks. That is all. Very simple concept. Okay. All right. Now let's go to the next thing, the understanding part. That why I have been reading all this. What is the discovery? Okay, what is happening in 2024? So let's see this. So what we saw that protons are positively charged, therefore have a magnetic moment, and neutrons have a magnetic moment too. Yet they are neutrally charged. So we talked about protons. We talked about the neutrons, and this is from an article that I took from newspaper, but I did the understanding part in the first go so that I do not have to explain all this again on here. Okay, so physicists in 1960s figured out neutron must be made of smaller particles. Which particles? Quarks. So now very easily understandable to us. But here note a fact that who named quarks? Who named quarks? Gell-Mann. Okay, he was a scientist, and the quarks were discovered in 1970s. All right. Now what we see that quark come in 6 flavors. These are known as up, down, charm, and strange. Up, down, charm, strange. top and bottom. These are all the quark particles that are making the other particles, subatomic particles. Okay, and they have a property known as the color charge too. And who was this Gell-Mann? What is the full name? Murray Gell-Mann. All right. So next thing, let's see that setting quarks free. The next heading in the article is setting quarks free. So there are 6 type of quark particles: up, down, bottom, top, bottom, strain, and charm. And each quark can have one of these 3 type of color charge. Then there are also anti-quark. They are antimatter versions. We do not want to go into antimatter right now. We do not want to go into antimatter right now. Most of the 80% of the energy in the universe is antimatter. Okay, we have only 20% energy as matter. Matter means, let's say, electron, but antimatter will be anti-electron, all right, or anti-neutron. They just have the same properties but opposite charges and so on. Okay, if they collapse into each other, then they neutralize and release a lot of energy. So this is the theory we have, because initially we thought that there is only energy in the world, only energy in the world, only energy in the world. Then how came matter? Okay, so what we saw, that energy was separated into matter and antimatter, and this is what made the particles. Okay, so even now we see that this is the energy particle theory. A very simple concept I will explain to you, that it will be difficult for you to think that how can energy change into particles? How can energy change into particles? Particles, we know, have a definite shape and size. Okay, so this is not true. Even the particle of any size, even us, even if we take us, so even we do not have any definite shape or size. Okay, if we go microscopically and zoom us ourselves, even our skin, then what we see, there will be electrons and protons flying like this. Okay, no separate boundary. And even if you are holding something in your hand, let's say you are holding a phone in your hand, so these particles, your fingers and the phone particles, they will never be actually touching each other. Okay, there will always be forces between the final particles of both the surfaces, and there will always be more repulsion force, okay, than the attraction force. So we do not have a definite shape and size. Okay, that is why energy can change into particles and so on. So matter and antimatter, very simple. Okay, this can be asked as a question, but just for the interest I told. All right, now a quark antiquark clump is also known as meson. Meson particle, very important. Okay, I told you this: up and down quark, up and anti-down quark. This is also known as a meson. Okay, they are also known as baryons. Meson is a baryon. All right, again, simple thing. These can be asked in the prelims again. All right, so please just know about all these things. Okay, 3 quark clumps, they are known as the hadron and so on, baryon and hadron, so on. All right, quark are further held together by another set of particle known as gluons. So we have already talked about gluons, another set of particle that determine the energies between up and down quarks. Okay, that make a proton or neutron. Furthermore, what we see, because nuclear forces are very strong, quark are always tightly bound and are not free. They cannot be found into isolation. But just now we saw in a quark star what was happening. They were existing in a continuous state of flow. Okay, even this was breaking. So this is a new discovery. Okay, one thing, that nuclear force that hold quark together explained by a theory called quantum chromodynamics. It predicts that at sufficiently high energies, nuclear matter can become deconfined to create a new part of matter in which quark do not have to exist in clump like this. So this what we saw where it was happening in the quark stars, and that is why it is hypothetical. All right, the further decayed state of a neutron star. One more thing, recently what physicists have been able to obtain, they have been able to obtain evidence of deconfinement in laboratories on earth. So they have even broken the basic clumping of the quarks. Okay, they have observed quarks in isolation. So this was an experiment known as the quark gluon plasma. Okay, this is a new state of matter, quark gluon plasma. So this is what we can find in a quark star, which we have not actually seen yet. All right, and now let's come to the next thing. All right, so according to Big Bang theory, the universe was filled with this plasma before the particles clumped and formed the first blobs of matter. Okay, so this is the base of the energy that we see, the energy that I was talking about, which converted into particles. So what was this energy? The energy was also made up of some particles initially. So these are the quark particles and the gluons. Okay, so this was the sort of state of matter that the Big Bang theory tells the universe was in. So if somebody asks you that what do you know about the Big Bang, what was initially in the beginning of the world, then there were quark and gluons. As of now, 2024, we know this. All right. So these were existing in this state, quark and gluon state, because the world was extremely dense as well as extremely hot. All right. Furthermore, it broke into particles, made clumps, became proton and neutron, and became particles. So this is the basis of all matter in life as we see it right now. One more thing you should know, that when we are talking about this quark gluon plasma state, so this is what we have observed till now. This can also further decompose into a black hole. Okay, there is more possibility than even these do not exist. But we finally do not know what is in the nucleus of a black hole. We still have no idea. Okay, because the gravity is so strong that we cannot see actually what is inside. So we have no idea that further than this what happens, at least till now. But as the future arrives, we will be knowing, of course, that what happens even when these quarks and gluons degenerate into just energy, or just let's say very high densely packed gravity. Okay. Okay, so that is all about the new things. Now just come to the pyq solution. Okay, so it wanted to talk about the cepheids first. Okay, CEPHEIDS. So what are cepheids? Cepheids are type of a star, first of all. They're type of a star, and they are a variable type of star. Variable means their energy or the shine that they produce is like this. It dims and brightens periodically. Okay, they are not giant cloud of dust or gas in space. Okay, these are sort of just stars, very specific stars. That is all about them. Okay, the first pair was incorrect. We'll come back. Okay, or just come back to the thing here only. Just a second. Okay, so cepheids are basically stars, type of stars. Okay, now come to the nebula. So you already know what is nebula. It's just a sort of a dust and a cloud in the space. Okay, we saw in the life cycle of a star, the first stage is the nebula only. Alright, so stars which brighten and dim periodically. Nebula is not a star. These are both different terms entirely. Nebula is just a stage before even a pre-star is formed. Alright, next we see what are the pulsars. Okay, do you know about pulsars? Pulsars are nothing. So let's say neutron stars that are formed when massive stars run out of fuel and collapse. So we talked about neutron stars, and pulsar are the type of neutron stars. They are highly magnetized neutron stars. Highly magnetized neutron stars, which emit beam of the electromagnetic radiation. Okay, so which appear as the regular pulses. What we see furthermore, that by emission of these pulsars, or these electromagnetic pulses, a neutron star can further change into a quark star, or a quark star can even further change into a black hole. Alright, we do not know exactly how this works, but as per the equation that we saw, this is how it works. Alright, so the neutrons star have tendency to release energy, and the sort of these stars are known as the pulsars. Alright, so pulsar, we can say neutron stars that are formed when massive stars run out of fuel and collapse. This can be true, this can be considered true, but this cannot be considered true, and this cannot be considered true. So only one pair is correctly matched. So this is the solution of the question we have. I hope you learned a lot in this lecture, and now you have fair idea about what are quarks, what are neutron stars, what are supergiants, what are main sequence stars, what are nebula, what are the let's say the globules of the dust. How does this all work? I hope you know now what are quark, up quark, down quark, and so on. What are lepton, hadron, baryon. All right. So multiple things. All right. When we talked about mesons, they are formed by the clumping of two. This is and matter and antimatter quark. All right, so very specific particles, they still exist in the world. We saw the generation of the quark and leptons. Much interesting thing. We saw the life cycle of a star. So very interesting thing for me as well as you, I hope. And we are further discovering what happens in the world as we come to more decades and centuries in this life. All right. So thank you very much. If you have any questions still, if you have any doubts with anything, then you can just ask in the comment section. If you have any feedback, you may share. Thanks a lot, and see you again in the next lecture. Have a great day ahead. Keep studying.